All right, in this video, I'm going to cover chapter 5, discrete probability distributions. So um, let's see what we're going to do in chapter 5. So yeah, here, this is a textbook. And then the objective of this chapter is to learn the definitely probability distributions with discrete random variable. But I know it's the what's the random variable, what's the probability distributions that we're gonna go over. I'm gonna go over that one, so don't worry about that. But so let's just figure out what I mean. The just see the blueprint in this chapter 5. Okay, so I'm gonna explain what we're gonna do in chapter 5, comparing with chapter 2 and chapter 3 what we have done. Okay, so the chapter 2 and 3. So as you can see that here, we use the real sample data to find the actual result. So then, so we collect for example, we collect the number of heads in tosses of two coin, summarize them in frequency distributions, and find the mean, exponent, and standard deviations. So which kind of we deal with the we just the using the sample data, and then we figured out the mean and standard deviations. uh these are we figured out mean and standard deviation. These are just actual result, right? And then you see that in the figure 5.2. So from the the event counting, I mean counting the number of head in tosses of two coin, we could get frequency distributions right there. So and then yeah, we figured out mean and standard deviation. You can see that here in the figure. In chapter 4, we learn about the probability, right? So the multiplication rule and the addition rule, and then conditional probability, and then rule for complement, okay, things like that, right? So and then now we're gonna combine all the concept we learned in chapter 2, 3, and 4 to find the expected result. Okay. So in chapter 5, you see that here you see the table here, similar to the frequency distribution, but actually not, because in the first column is exactly the same as the column in the frequency distribution, but the second column, the frequency distribution, second column represent the frequency, right? Number of the number of outcomes, right? So but in table that in this table in chapter 5, you can see that the second column represents the probability. So we want to figure out the probability that we will get 0 head, and then first just 1 head and the 2 head. Okay, so this table is the example of the probability distribution. So probability distribution is actually the kind of table or graph showing that the probability for each outcomes. Okay, it's possible outcomes. So now in chapter 5, we're gonna use probability to find the expected result. Okay, so we don't deal with we're not gonna try to find the actual result. Okay, we will find the expected result. So that's the big picture of chapter 5. All right, so now the I'm gonna cover chapter 5 point section 1 and section 2 in chapter 5. Okay, I'm not gonna cover section 3. And then section 1, yeah, definitely we're gonna learn about probability distributions. First, we're gonna um, define random variable and probability distributions, and then we determine when a possible probability distribution actually satisfy the necessary requirement. So in order to be a table represent probability distribution, what kind of conditions must be satisfied, we'll learn that. And then given a probability distribution, compute the mean and standard deviation, and then use those results to determine whether results are significantly low or significantly high. We learned that was significantly low and significantly high, right? So, but we'll see again, okay? And then, yeah, so compute the mean and standard deviation. Yeah, we gonna compute this one using the calculator, okay? TI 84, okay? TI series calculator. So Therefore, I'm going to introduce the formula, but yeah, you don't have to use it. Okay, just but instead of that, I'll let you know how to find find out them using calculator. The section two, we're going to study a specific not popular, but specific probability distribution. It's called binomial probability distribution. Okay, so what is this? We learned the definition of binomial probability distributions. Okay, and then we're gonna find out the mean and standard deviation of binomial distributions. Okay, and then we use those results, excuse me, to determine whether results are significantly low or significantly high. Okay, so let's see the section one. Okay, let me use the PowerPoint lecture slide instead of the handout. All right, so first one, random variable. What is the random variable? So random variable is a variable, okay, that has a single numerical value determined by a chance for each outcome of procedure. For example, so the think about this. The yeah, simple example, just when you're tossing a coin, okay, so the two times, okay, or is you just tossing two coins, for example. Okay, let's say just tossing a coin, tossing two coins, and then we want to count the number of heads. Okay, so now then we can expect that possible outcome going to be 0, 1, 2, right? So from the event, we get the numerical value representing possible outcome 0, 1, 2. 0, 1, 2 are numerical value, right? So the random variable, in that the event, random variable represent the what number of head. So it's so random variable should have what must the must be a real number, right? 0 or 2, 0, 1 or 2, right? Okay, so as you can see that here, random from the event, or I mean from the experiment, sorry, experiment, the converting the possible outcomes as the real number. Okay, and then the random variable the value random variable will be those real numbers. Okay, so now we understand it, right? So next one, the probability distribution. I told you probability distribution is description, normally table or could be graph. Okay, but we very most of cases we're gonna deal with a table as probability distribution. So description that gives the probability for each value of the random variable. Okay, so it's often expressed in a format of the table or formula or graph. So now the discrete random variable. Okay, so there are two type of random variable: discrete random variable, the continuous random variable. Okay, so as you may uh, figured out already, discrete random variable has a collection of values that is finite or countable. Okay, so now, for example, a number of heads is discrete. Okay, so and then the number of card this should be discrete. Okay, so now then the number of value is countable, and if it is possible to count them individually, such as number of tosses of coin before getting head. Yeah. Okay. Then continuous random variable has infinitely many values, and the collection of values is not countable. Okay, so that is, it is impossible to count the individual items because at least the sum of them are on a continuous scale, such as body temperature or the time. Okay, something like this. Okay, so let's see more example about the continuous random variable, discrete random variable in my handout. Okay. All right, let's do this example. So let's figure out each example uh, is a discrete or continuous or not a random variable. Okay, so eye color. So the eye color, yes, then could be a brown or black or the purple or you know the black, something like that, right? So but the is that discrete? No, it's not countable, right? It's actually the possible outcome is a categorical, right? Not the real number or not a real number. So actually, I color is not random variable. Okay. So it could be to be the random variable. The possible outcome can be converted to a real number. Okay. And the height, yeah. So is that the okay, definitely height. Then possible outcome must be a real number, right? Then what? Is there a then we have two choices, right? Is this a discrete random variable or a continuous random variable? It should be continuous, right? So all the measure must be continuous, okay? So this is continuous. That is a discrete. Okay. And then number of passenger on an airplane. So number of passenger, so we count the passenger, right? It's countable, so it should be discrete. Okay. And then political party, as GOP or Democratic, so it's not a number. There's not number a category, right? So it's I'm sorry, this should be is not a random variable. So this is also not a random variable. Exact cost of large pizza. Yeah, is exact cost of large pizza. It should be discrete, right? Okay. So now then move to the lecture slide. Now let's see probability distribution requirement. So every probability distribution must satisfy each of the following to the requirement. First one, there is a numerical, not categorical random variable x. Okay. So simply saying that the probability distribution, I mean, using the table, okay, as example of probability distribution, the table should consist of two columns, and the first column represent the possible outcomes or possible values of random variable, and the second column must be their corresponding probability. Okay, so there is a numerical random variable x, and each number values are associated with the corresponding probability. And then the sigma p of x, it means that what? The sum of all the probability must be equal to 1. Okay, where x assumes all possible values. And the sum of all possibility must be 1, but some such as 0.999 or 1.001 are acceptable because they result from rounding errors. Yeah, okay. But yeah, so the key point is sum of all the probability in the table of probability distribution must be equal to 1. Otherwise, you did something wrong, or that that table is not a probability distribution. Okay. And the last requirement is this: for each values of random variables in the first column, the probability must be between 0 and 1. Okay, for every individual value of random variable x. I told you. Let's see example. I know it's a little bit abstract, right? So let's see example right here. Example 1. um let's consider the tossing two coins with the following random variable. Okay, x is the number of heads when two coins are tossed. Then the can we say that x, the letter x, as a random variable? Yes, number of heads when two coins are tossed. So the x, you know, the value of the x must be integer, right? 0, 1, or 2. Because in an experiment, we're tossing a two coins. So the possible outcome must be 0, 1, or 2, right? So x can be a 0, 1, or 2. So x must be a real random variable. Now we see that here table right there. So first column is what? The represent the values of random variable, and the second column represent probability. Okay. So now why is 0.25? Probability that we get zero head is 0.25. It makes sense, right? Because possible outcome is what? Head, 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 tail, tail, head, and tail, tail, right? So there are four out of four possible outcome. Excuse me. There is only one outcomes doesn't have head at all. Excuse me. So 1 or 4, this is a 0.25, right? So now the 0.5, yeah, it makes sense. Why? Because there are two outcomes has only one head out of four outcomes, right? So 2 over 4, which is a 0.5, right? Now the example 1. So we can check all three, whether or not we can check whether or not all this table satisfy all three requirements. Okay, so definitely makes sense because all the variable x is a numerical random variable, yes, and then sum of all the probability equals one, yes, and then each value of probability p of x represent probability of at probability of the specific random variable x. Okay, so now example, so yeah, so random variable x in the table is discrete random variable because it has three possible values, and the three is a finite number. So this satisfies the requirement of being finite. Yep. And then sometimes you see the probability histogram. This is similar to the relative frequency histogram. Okay, but the vertical scale show probability instead of relative frequency based on the actual sample result. Okay. So it's not just a regular histogram, okay, probability histogram, okay? You see the vertical axis doesn't represent frequency or nor the relative frequency, so but probability, okay? So that's the one of the example of the one of the way to represent probability distribution. Yeah, this is example of probability distribution as a graph. Okay. Now the probability formula. Okay, so see, probability distribution could also be in the form of formula. Consider formula like this: 1/2 times 2 minus x factorial times x factorial. You know, see the exclamation mark? We learned about this, right? Factorial. Okay. So now, what's the factorial? Then here, so for example, the 5 factorial means that 5 times 4 times 3 times 2 times 1. Okay. So it means that n factorial is equal to n times, okay, n minus 1 times n minus 2, okay, and so on, up to 1, okay? So keep in mind this. So that's the meaning of factorial. So you can calculate the factorial of using calculator. I'll show you. So in a calculator, so we go to the map, okay? So here, this map, click. Then there is a 4 tabs: math, a number, complex, probability. We go to the probability. Okay, and you see that here, factorial right there. Okay, so we use this one. So to do that, let me figure out the 5 factorial. So enter 5 and then go to math and then probability and the factorial. Enter. Okay, click it. So we got 120. Okay. All right. So I don't know where that formula comes from. Just an example. Okay. Then we find that P of 0 is 0.25 and the P of 1 is 0.5. By the way, 0 factorial and 1 factorial equals 1. Keep in mind this. It's quite important. And then most of students just forget about it. Okay, 1 factorial equals 1 and then 0 factorial equals 1. I mean, 1 factorial definitely equals 1, right? But why 0 factorial equals 1? Yeah, it was mathematicians just defined that, okay? So that's beyond of the subject, so I'm not going to explain about detail why zero factorial is 1, but just subset that. Okay, so now p of 2 is 0.25. Okay, you just, if you interested, just try to figure out why really, you know, p of this formula return 0.25, 0.5, 0.25, but actually it does. So now then, you see that this is exactly the same as what the oops, that result, right? P of 0, P of 1, P of 2, right? Okay. So now in this experiment can be uh, the expressed instead of the table like this, but formula like this. Okay, that example of the what probability distribution, the way to express probability distribution as formula. Okay, so now the this is example 2, job interview mistakes. So the hiring managers were asked to identify the biggest mistake that job applicants make during an interview. And the table below is based on their responses, based on the data from the ethical survey. Okay, so does the table below describe a probability distribution? So yeah, it looks like the, this table describe the probability distribution, but you see a total. I mean, the sum of all problem must be equal to 1, but that exceed, right? 1.57. So I don't think that this is the probability distribution that doesn't that describe probability distribution. No. And then you still look at the values of random variable x. It's not a number. It's a categorical value, right? So I don't think that this is the that describe the probability distribution. So solution: the table violate the first requirement because x is not numerical random variable, and then so second, that table doesn't satisfy what the second requirement. Some probability equals 1. See, right? Now the next one, parameters of probability distribution. So one in here, we deal with the population probability distribution. Okay, so the values of mean and standard deviation and the variance are parameters, not statistics. Okay, remember that the difference between parameters and statistics. So parameters is what the characteristic of population, and statistic is what the characteristic of what sample. Okay, so now in chapter 5 we deal with what? Oops, excuse me. We deal with the population. So all the mean, variance, standard deviations are actually parameters. So mean variance, we see that standard deviation is the definition it is for the probability distribution. Okay, so mean gonna be, we use a Greek letter mu, is the sum of all the x times the p of x. Okay, variance is gonna be x minus mu squared times p of x, the summation. The sigma represents the sum. Okay, you don't have to memorize this. Okay, so yeah, just look at it. Okay, right? So mean is what? Sum of all of the terms, numbers obtained by x times p of x, and this one sum of all the numbers obtained by x minus mu square minus p of x. I think this is uh, give me a second. Yeah, it's just typo. Actually, x minus mu and then close parenthesis and then square. It's typo. Okay. It should be x minus, I told you x, let me tell you again, x minus mu and then close parenthesis and the square. Square must be out of this parenthesis. Okay, it's typo. So now the standard deviation is what? Square root of variance. So, okay. So now then, and the expected value. So the expected value of discrete random variable x is denoted by e, and it is the mean value of the outcome. So expected value is nothing but mu. Okay. So see that that's the definition of expected value. This is exactly the same as what the definition of the what population mean. Okay, let's see example 3. So back to the same the table probability distribution what we saw in example 1. We want to find out mean, standard deviation. Okay, but then why have to use, yeah, so here in the lecture slide they they figure out by hand. See, they just figure out x times p of x for each random variable, value of random variable. Okay, and the x minus mu squared times p of x, right? But let me figure out mu and the sigma using calculator. Okay, first what you're gonna do, you need to enter the what values of random variable and then their corresponding probability. Pretty much you have to enter the first column and second column in the calculator separately. Okay, so we go to the stack. Okay, so and then to enter the data, we go to edit. Okay, so I already entered the 0, 1, 2. This is the possible values of random variable, right? In L17, and then next column L18, I enter their corresponding probability. Okay, once you do this, then we go to the stack. Okay, and then go to calculate, and we do one variable stack. Okay, so one variable stack, and then we enter the L17, which is the list of what values of random variable. Okay, the frequency, you enter the column name of the probability. Okay, so we calculate. And then you see that here, the sigma, wait, sigma x, I mean x bar. That's the actually Yeah, I know X bar is what symbol of the sample mean. But since we know that we deal with the population, so it's actually this is a mu, okay? So mu equals 1, okay? So expected value is 1, okay? So what's the expected value? What does that mean, expected value 1? It means that in that experiment, tossing a 2 coins, we expect that what and based on the statistic, we expect that we're gonna have 1 head, okay? That's the meaning of x bar equals 1. I mean mu equals 1. Sorry. And then sigma, you see the sigma x, that's the standard deviation, 0.707, 106. Okay. So that's the standard. Then how can you find the variance? Take a square. Keep in mind this. Standard deviation is what? Square root of variance. Okay. All right, so back to here. So yeah, example 3, they got the same result. See, mean is 1 and the variance is a 0.5. Oh, I thought we got the 0.7. That was a standard deviation, okay? You see that here? Standard deviation 0.7, 0.707107. This is exactly the same number what I got using calculator, okay? And then actually taking square, we're gonna get the what? Taking square, you're gonna get the 0.5. So variance is gonna be 0.707107 square, which is 0.5, okay? So now the example 3, finding the mean variance and standard deviations. I mean, yeah, so it's the interpretation. So when tossing 2 coins, the mean number of head is 1 head. The variance is 0.5 square, head square, okay? So, and the standard deviation 0.7 head. So also the expected value from for the number of heads when 2 coins are tossed in 1.0 head, which is the same value as the mean. So if we were to collect data on a large number of trial with the 2 coins tossed in each trial, we expect to get a mean of 1.0 head. Okay, so now the next one, significantly low and high. We learned it, right? So I'm sure that you have seen this one. So what does that mean? Significantly low value, which means that the value is less than mu minus 2 sigma. Okay, I mean, just look at this. Just make the give me a second. So we just drill two vertical line. Okay, mu minus 2 at mu minus 2 sigma and then mu plus 2 sigma for each. Now all the value outside of that the range interval mu minus 2 sigma and mu plus 2 sigma, all the value here gonna be significantly low, and then all value beyond the mu plus 2 sigma gonna be significantly high value. Okay, that's a pretty simple, right? So now then next one. So let's see. Example 4. So identifying significant reserve with a range rule of thumb. So we found that when tossing 2 coins, the mean number of heads is 1 head and the standard deviation is 0.7. Use those results and the range rule of thumb to determine whether 2 head is a significantly high number of head. Let's see. So first one, you need to figure out the mu minus 2 sigma and the mu plus 2 sigma, right? Okay. Give me a second. Yeah. The significant high number, just want to check that 2 head is significantly high number. Then it's okay. You just figure out mu plus 2 sigma, okay? So mu plus 2 sigma gonna be 1 plus 2 times 0.7, which is 2.4. Then 2 head is significantly high? No. Okay, so because 2 is not the above mu plus 2 sigma. So based on this result, we conclude that 2 head is not a significantly high number of head because 2 is not greater than or equal to 2.4. Yeah, you see. Now, next one, the identifying significant result with the probability. So the significantly high number of successes. So let's see. X successes among n trials is a significantly high number of successes if the probability of X or more successes is 0.05 or less. Okay, so that is X is a significantly high number of successes if probability X or more is less than or equal to 0.05. Okay, you understood that. So okay, for example, so somebody just they won the lottery 10 times. It's just maybe, I know in common sense it's maybe kind of kind of impossible, right? So the probability that somebody just get won the lottery more, more than 10 times, and using common sense, it must be what significantly high, right? That's too much, right? It's kind of unfair, right? So now the probability of that gonna be what, less than or equals 0.05. Okay. So the if yeah, I mean statistically, probability that x or more value is less than or equals 0.05, that we say that we say that what the x is a significantly high. Okay. So oops, excuse me. Now then, significantly low number of successes. X successes among n trier is significantly low. Then what if probability that x or fewer is less than or equals 0.05? Okay, we're gonna revisit this one next time. Okay, later. Okay, so just keep in mind that. And then rare event rule for inferential statistic. So if under a given assumption, the probability of a particular outcome is very small and the outcome occurs significantly less or significantly greater than what we expect with the assumption, we conclude that the assumption is probably not correct. Yeah, so that's the real event rule for inferential statistic. So, and the next one, expected value. But don't worry about this. The significantly less or high, we're gonna see, okay, later. So expected value, it is. I told you this is exactly the same as the formula. Is exactly the same as the mean, right? So let's see example 5. So you have $5 to place a bet in a Golden Nugget casino in Las Vegas. You have narrowed your choice one of the two bets. Okay, so roulette, a bet on the number 7 roulette, and then craps the bet on the pass line in the dice game of craps. So now see, if you bet at $45 on the number 7 roulette, the probability of losing $5 is 37 over 38. You see that the the probability of losing $5. So losing means what? Negative minus 5, right? Negative 5. And then 37, 38, that's a probability that you're gonna lose $5. So 37, 38 is actually probability of that random value of random variable 5. And then the probability of making a net gain of 175. So net gain of 175, that's a plus, right? And then 138, that's the probability that you can earn 175, right? So 1/38, this is a probability of the random value of random variable 175. Okay. So the price is 180, then including your $5 bet, also the net gain is 175. Okay. Find your expected value if you bet $5 on the number 7 roulette. Okay. So what you're gonna do? So now, give me a second here. Yeah, see the solution, question A. So roulette, the probability and payoff of being betting $5 on the number 7. Okay, so now, so we try to describe this one in as a probability distribution table of probability distribution. Okay, so first column represent the positive values of random variable. Okay, -5 and then positive 175. It makes sense, right? The probability for each random variable gonna be value of random variable gonna be this fraction, right? Now we're gonna enter these. I mean, I don't think only two. We have only two rows, so I don't think we. Um, I think we can just do by hand, right? I don't think we have to use a calculator. So using the but if you don't know the formula, if you okay, so it's so confused, then it's okay. Just use calculator, okay? So and then anyway, so expected value gonna be the sum of all the x times p of x, okay? So -5 times that fraction, which is this, and then 175 times that fraction is returned that number, and then adding them up, we're gonna get minus 0.26. So you're gonna lose, you're gonna lose 26 cents. That is for every $5 bet on the number 7 you can expect to lose. on average of 26 cents. Okay, so now this is yeah, now see the B question. If you bet on $5 on the pass line on the dice game of the craps, okay, so the the probability of losing $5 is that fraction. See, 251 over 495, and then probability of making a net gain of $5 is a 244 over 495. So now the find your expected value if you bet a $5 on the pass line. Okay, then the okay, the probability you're gonna lose $5 is this. The probability that you're gonna win the $5 is this. So we're gonna find out x times the p of x for each row. Adding them up, you're gonna get 0.07. So it means that what? For every $5 bet on the pass line, you can expect to lose an average of 7 cents. Okay. So now the what's the conclusion then? Okay, so the $5 bet in the roulette result in the expected value is a negative 20 cents, while 7 cents for the passing a line. Okay, so because you are better off losing 7 cents, definitely. So the scraps game is better in the long run. So even though the roulette game provide an opportunity for larger payoff when playing the game once. Okay. So this is how the use the statistic in the betting game. Okay. So that's all of this section 1. Okay. Next time I'm going to cover up the section 2, 5.2. I mean. Okay. Let me stop here.